are going to listen to Nick Swamy of Microsoft Research and the Joint Center MSR in RIA. And he will talk about the new version of F-star with dependent types and effects.
Thank you, Tahina. Thanks for coming after lunch. This is joint work with lots of people, including Catalin, who's there in the room, and we're both around for most of the week, so you can pester us with questions. But there are lots of other people as well, whose names I won't read all their names, but F-star is an open source project, so if you're interested in this stuff, we'd be happy to have your contributions too. So this list may even grow longer, maybe. Right, so what is F-star? It's a framework for verifying ML-like programs. So ML-like in the sense that it's higher order, it's effectful, and it's called by value. And it's highly customizable, so very little is baked into F-star. Most of its semantics is governed by libraries that define the semantics of the effects that are in the language. And it's one of the things I'll try to emphasize in this talk is that it's easy to experiment with F-star, changing various bits of the way the language is set up by choosing different memory representations or different effects and so on. To give you a first taste of F-star on a very simple program, you write factorial like this. The syntax looks a bit like F-sharp or Camel Light. And you can give it a specification. This specification says that factorial is a total function, which if you give it an integer greater than or equal to 0, it's going to give you back an integer that's greater than or equal to 1. So the tot there on the arrow to the right of the arrow, it indicates that it's a total function. And then you can ask F-star to check it, and it checks it, and it's happy. Under the covers, what happens is that in some context that's defining the semantics of the base effects in the language and so on, F-star type checks the factorial program, builds a type for it that checks that the type is compatible with the type that the user claimed. This produces a VC, a verification condition, here the formula phi, which we then pass to Z3 to check validity. And if the check succeeds, then from the meta theory of F-star, we conclude that that program is safe at the type T. So please interrupt me as I go along with questions.
Should we read the left narrative?
Sorry?
Should we read the left?
Under the condition phi, the program factorial n equal t has type T in the context gamma. So we've been working on F-star or languages like it for some time now, starting with some languages before the line of work that we've begun. Some of these may be familiar to you, things like Cayenne and so on. But in the last year or so, we've done a complete redesign of F-star and are now progressing towards a 1.0 release of F-star. And I'll speak mainly about this latest version and mention in a few places how it contrasts with the prior versions. So F-star currently in 2015, you can think of it very roughly, and there are many technical differences, but very roughly you can think of it as Hoare type theory with refinement types and an SMT solver in the back to give you automation. Revealing some details, unlike Hoare type theory, effects in F-star are primitive, so we run like in ML with primitive state and exceptions and I/O and so on. Instead of using Hoare types, which are these triples, under the covers, effects in F-star are really specified using a lattice of predicate transformer semantics. So we take predicate transform semantics as the primitive notion and build Hoare triples on top of it. Instead of having just one effect, we have a lattice of effects, and there are monad morphisms among these predicate transformers that build the lattice. We do semantic termination checking. So as opposed to relying on, say, like a syntactic godliness condition in Coq, termination checking in F-star is done semantically with respect to a well-founded ordering that the language includes. We do type and effect inference. We have SMT solving in the back for large boring proofs, but SMT solvers are really only good for large boring proofs. For intricate proofs, SMT solvers can go off the deep end, and so we let you write dependently typed programs as proofs inside F-star, and you can use that as an alternative to SMT for more elaborate proofs. F-star is open source. It's written in F-star, so it bootstraps, and it bootstraps into OCaml and F#, and it's available on all platforms. We have binaries on all platforms, and we made a fresh release just yesterday, or maybe 2 days ago, so you can give it a go. What we've used this new version for so far, so we have about 45,000 lines of verified code in our there's sort of a few main applications of it that I'd like to highlight here. One is we use F-star as a proof assistant, and perhaps the largest development we've done so far is to mechanize the meta theory of a subset of F-star, which we call micro F-star, and we've mechanized it in F-star. That's maybe, I think, maybe a 6,000 or 7,000 line development of F-star and F-star. We also have used F-star as a host for several embedded DSLs. So a couple of things we've been doing recently. We have a model of region-based memory management inside F-star, and we compile to OCaml, linking with a native library that we wrote in C that we access via OCaml's FFI that provides us with a region-based memory manager in OCaml. So we use a mixture of GC and regions in OCaml and prove at the F-star level that you never access a pointer to a region that's been deallocated, for instance. We also have another instance of a fairly large development is a DSL and an interpreter, and the interpreter is verified in F-star, and the interpreter provides an implementation of a distributed secure multi-party computation execution model. And over the years, the largest uses of F-star have generally been for verifying crypto protocols, and we continue to use F-star for that, and currently we've adapted a prior implementation of TLS 1.2 to F-star and are improving it and trying to extend it to cover TLS 1.3. So we've taught several courses on this stuff so far. There's lots of online material on our website, including an online tutorial. Catalin and I are doing another tutorial on Friday at CUFP. So do sign up, and you may get one of these T-shirts if you do. So maybe that's motivation. All right, so what I thought I'd do for the rest of this talk was start with a little bit of background on refinement type systems and highlight some of the motivation behind this redesign of F-star. And then I thought I'd just do several examples to give you a flavor of the system, trying to avoid too much technical details about the way the system is set up and really give you a flavor of how F-star works instead. So dependent refinement types. So there have been many systems that provide dependent refinement types, the predecessors of F-star being some of them, but also things like liquid types, maybe some things like what Michael was talking about earlier with manifest contracts. And in general, the way these things work is that you have a type, people write it differently. We write it this way with the formula phi being a refinement of the type T, and the terms that inhabit this type are values of type T that also satisfy phi. And this is useful to state many simple properties. So you can do array bounds checking and overflow and so on by adding refinements of this form. You can define UN32 as to be a refinement of int that looks like that, for instance. And when you use things like integer inequalities, SMT solvers are really well tuned to handle this, and you get pretty good automation. But as you add effects to the language, things get a little bit trickier. So, if these expressions are just expressions in the language, what do you do about refinements like this that maybe mutate the thing that you're refining? And maybe Michael wants to do some stuff like this, but so we think of this as, this is just bad. You shouldn't be doing this. And most prior languages rule out this kind of stuff. Usually just by syntactic fiat. Just say, okay, this stuff, so in F7 and F stars, the prior versions, the restriction has been that these formulas have to be values. And that just straight away rules out all effectful stuff. In liquid types, I think you can write non-values there, but the non-values are just uninterpreted. So morally, they're just like values anyway. This makes for quite a simple theory, and it's still reasonably expressive. So we've done a lot of stuff with just value dependency in the past, but it's too simple. So here's Here's some example of showing you how this stuff falls down. So if you have just the identity function, well, you can prove that 0 has the type, the singleton type 0. But if you apply ID to 0 and you want to prove that the thing still has the type 0, the singleton type 0, where ID just has the type int arrow int, this usually does not work in prior systems. What you need to do is to actually enrich the type of ID, recording in its result type that it in fact is the ID function. Which for the ID function is perhaps okay, but you can see that this quickly starts to get terrible. Like if you write, say this is the function taking the absolute value of things, and now you have to enrich the type of the absolute value function with some logical lifting of the body of the thing, just so that you can prove the property that you care about. So you can imagine that as this gets larger, this style is just, it's really painful. So in F-star now we have a semantic treatment of effects, and we no longer have any special value restriction. And you can now write the type of ID applied to 0 is just the integer refined with this equality saying that it's equal to ID applied to 0. And then you can just compute with ID applied to 0 in the types and show that this type is equal to this type and get the thing that you want. And likewise for the absolute value function. Now, to make this sensible, we still have to restrict phi to be pure things. And so we have a semantic check for purity. And that leads us to needing to isolate a language of pure total functions inside a language with effects. So the way we do this is by introducing a lattice of user-defined primitive effects. So this is the way, so I want to emphasize that these are primitive effects. The effects are built into the language, but the user gets to stratify the effects according to a lattice of his choosing or her choosing. So if you're only interested in, by default, you may just only be interested in pure things, and all things may have all the effects of ML. And maybe you want to configure F-star this way. But you may also want to have a finer notion where you say, I separate out divergence from exceptions from state, and you can carve out the effects in this way as well. Yeah.
It has to be a sublattice of this one.
Sorry?
It has to be a sublattice of this one.
It could be a, no, it just, the constraint that we have is you have pure at the bottom, all at the top, and you can carve out the middle. Sorry?
It has to be always lower than DFXN, right?
It has to be.
It has to be compatible with these.
That's right, yes. So we require these to be monad morphisms. So if you try to switch things around, it would no longer be a morphism. And in fact, when we run F-star, we actually configure it with some more points in this lattice to separate out ghost code from non-ghost code, this kind of thing. And each of these monads is equipped with its own weakest precondition calculus. And these morphisms are really morphisms among the weakest precondition calculi. So for example, if you write a pure term like 1 plus 1, this has the type and effect tot int, meaning that it's unconditionally pure and always returns an int. You can have conditionally pure things, so you can say factorial is pure, it returns an int as long as you can prove that x is greater than or equal to 0, and you know that, well, if it returns, it will always return, and it returns a y that's also greater than or equal to 0. And by subtyping, you can show that factorial of 1 is unconditionally pure, returning a nat. For stateful things, there's another effect. The indices for stateful things have a different shape than they do for pure things because you speak also about the heap. And so for x applied to, assigning 17 to x, you have something that says, well, for example, you could say, in order for this to be well formed, you have to show that the heap actually contains this reference and that after you do the assignment, the heap is updated appropriately. It's a call by value semantics. So what we have is every arrow has a monadic codomain, and it's a monad with a result type and then an arbitrary number of indices depending on how that effect is defined. What this means is that we have a number of defaults. So for curried functions, we write curried functions where all the intermediate arrows are always tot, and the final arrow has an effect on it. And if the effect is omitted on the final arrow, it defaults to the ML effect. So if you write just an ML type, it just looks like the final arrow can have whatever effect ML allows you to have. So those are defaults that we pick because we want to interoperate with ML. Let's start with how we do semantic termination proofs. So F-star has a well-founded ordering on all its terms. The way we set it up is that it includes a subterm ordering on inductive data. It includes Lex orderings and the ordering of NATs. And we also have things like, the codomain of the application. The result of the application of a total function is smaller than the function itself, this kind of stuff. Which lets us to write programs like this. So if you have a tree, an n-array tree, and map being your usual map, except decorated with totes to indicate that it's a total function, then you can write tree map like this, where you want to just use map to map the function over the children, and you can, and the way you express to f star that this is okay is that you do the map at a type here that says, I'm going to map this function over all trees that are smaller than the tree that I'm doing my induction on, which is the thing that expresses to f star that something is always decreasing on every call. Unlike, I think in Coq, you couldn't really do this except if you unfolded the definition of map and then you noticed that the recursive call was happening on subterms. Here you express it just using the well-founded ordering on types, on terms. Here's what quicksort looks like, a simple one in f star where you take the head element to be the pivot. It's the normal implementation, and you can write a spec for it that looks like this. It says pound indicates an implicit argument in f star. So A is an implicit type argument. If I have a f, which is a total order, and a list, I get back a list that's sorted and that the occurrence counts are preserved. And to express the termination of quicksort, this is the metric that decreases the length of the list on each recursive call. Notice that in order to do this, I take just the standard list library. I haven't changed the definition of any or the types of any of of anything in the list libraries. Append has just got its normal type. Partition has got its normal type, so on, except decorated with totes in various places. And even total order is not really built in. You can write refinements of functions. Some prior systems forbid this, but here you can have a function f, and I can add a refinement on it saying that it's a total order. That's fine. But now notice that I just took the standard library as it was with its normal ML types in some sense, and I now want to prove this stuff about quicksort. The way that I do it is by a mixture of this kind of intrinsic and extrinsic proving, where by extrinsic proofs I mean that you have a pure function and after the fact you prove some lemma about it, and then you can make use of that fact when you use the pure function. And intrinsic proofs are when you enrich the type of the function as you define it then and there. So here, in order to complete this proof of quicksort, what we do is, in the case of append, for instance, we need this lemma. And this lemma is a lemma about append that's very specific to quicksort. What it's trying to prove is that if you take a list L1 and you append it to a list where you have the pivot in the middle and a suffix, then under some conditions, this list is also sorted. Now, this is very specific to quicksort, as you can imagine. And you don't want to enrich the type of append with something so specific to quicksort. You'd like to prove after the fact that it has this property and make use of it in your proof of quicksort. So f star lets you do this. But in prior systems that have had this feature that lets you prove properties after the fact, you typically have to go in and then also, for instance, when you actually say call append here, you may actually have to also make a call to the lemma to get the property that you've proven about this thing after the fact. So f star gives you a way to avoid having to pollute your definitions with these lemma calls by relying on the SMT solver. So when you do sorted app lemma, having proven your property, you can add this annotation that says, hey, SMT solver, whenever you see a term of this form among in your context, you have this lemma to make use of. And this lemma is available to the SMT solver as a big quantifier. And then the SMT solver will instantiate the lemma as it needs. So this is a way to kind of inject properties to the SMT solver extrinsically after the fact and keeping your definitions unpolluted. So for the rest of the talk, I'd like to talk a little bit about how we do how we have some flexibility when we do stateful verification. The example that I'm going to present is a little toy example, but it's kind of motivated by how we reason about heap invariance over multiple structures when trying to verify this TLS implementation. So the example is a little toy. It's about some flying robots. I don't know if some of you have seen, recognized this image from a Japanese TV series some years ago, but if you do, you might appreciate that. But So the idea here is that we have this very simple model of a flying robot where a robot just has a position and two arms. And our robot has an invariant that whenever it's flying, its arms are up. The thing I'm going to try to prove is some kind of a very simple framing property where if I have two robots and I make one robot fly by sticking its arms up, if I have some other robot in my context that's not flying, I'd like to know that this one didn't stomp on the other one and the other one is not flying. So it's a very simple but classic kind of framing issue. So F star is using an SMT solver. By default, we don't our assertion language over stateful things is not separation logic. It's a classical logic. So how do you specify this kind of thing in F star or tools like it, maybe Daphne and other tools and so on? So in order to do that, you need to have several kinds of anti-aliasing properties. So for instance, you need to know that, all the refs in one robot do not overlap with the refs in the other robot. And that's a quantified invariant that you need to have around. Well, it gets worse because you also need to say that all the refs in the left arm are disjoint from the refs in the right arm and are disjoint from the refs in the position of the robot, all of which gets pretty clumsy. So one symptom of this, one cause of this problem is because we're verifying everything with respect to a flat model of the memory where you just have a flat heap. But F star lets you impose an abstract user-defined memory model on top of this flat heap model. And one of the ones we've been experimenting with recently is something that we call HYPER-HEAPS, where you have your concrete heap at the bottom, but you overlay on top of it an abstraction where you split the heap into several regions, several disjoint regions, and each region has a region identifier, where the region identifiers are organized in a tree-like namespace. So the region identifier 0 can be used to speak about ownership of all the regions in this subtree, for instance. So we overlaid this kind of hyper-heap structure on top of the vanilla flat heap. And the way we do it is just by writing a new module saying we have some type of region IDs. And you can think of a region ID as just a list of natural numbers. And now our memory model is memory layout, instead of just being a heap, is going to be a map from a region ID to some heaps. And we provide some theory over these region IDs, some inclusion and extension and so on. And then we provide a type of references which we called region references, where region references are like references, but they also mention the region into which they point. And you can give a select update theory over region references and hyperheaps, which is, as you would expect, it's dereferencing in the map first and then in the heap again, and you get a select update theory on hyperheaps. And once you do this, you can package it all up as a new instance of the state monad. So you can say, I have a hyperheap state monad, and it's an instantiation of the state monad where you take the type of the state to be the hyperheap model as opposed to the vanilla heap model. And then you can just define a bang and assignment to work over hyperheaps as opposed to working over normal heaps. Technically, in order for this to be admissible, you have to prove that the hyperheap model is isomorphic to the vanilla heap model, because the hyperheap is just an abstraction, whereas you run over using the flat heap. So we do that, and we show that this model is admissible. And once you do, you can define the example that we had before. You can say, when I allocate a point, I'm going to allocate it in a particular region, and all my references are going to be in that region. And similarly for the arm of the robot. And when you build the bot, you can say, it has a position, a left arm, and a right arm. And you have an invariant on it saying that, the regions of each of these sub-objects are all disjoint. Okay. And that suffices to then write your program this way, where you say, I wanted to make two bots fly, so I take my two bots. I have a precondition that they live in disjoint regions. And I have a precondition saying that they're both initially satisfy their invariant, and I just fly both of them, and I can show that that at the end they're both flying, they both satisfy the invariants, and the only things that have been modified are each of their regions, which is much more compact and actually much more efficient for the SMT solver to prove than having all these quadratic number of inequalities among the references of the two bots in your context. Just to give you a quick demo of how this looks. So this is F star in an interactive editor. And you work with F star this way in Atom editor in a proof general style mode. And there you go. So that's something you can try out as well. I'm mostly out of time, so I'll leave this up there. And if I have time for questions, I'll take some.
When you specify this the subtype, the language of the predicates, does it match the actual language you're programming in, or is it a different one?
It's all the same. Okay, the question was whether the language of specifications is the same language or a different language.
Yeah.
It's the same language, so it's a dependently typed language, and the language is the language of specifications is just the language of types.
Okay, so on the first slide you have an example of X of type int 32 or something.
Yeah.
You said that must be less than 2 to the 32.
Yeah.
So 2 to the 32 doesn't fit.
Yeah, so the refinement is over, it's a refinement of int, and int is mathematical integer.
Okay, so you have some sort of mapping from the language's
Yes.
functions into...
So we have, yeah, so it's mathematical that if you want to use bounded, you want to check bounds, then you use the bounded version of integers and the bounded exponentiation and so on.
Okay, so there's two classes and so on.
Yeah. Yeah, because they're two different types in some sense. Yeah. Yeah.
You mentioned ghost.
Yeah. So that's for purely specificational things. So you may want to have some computation like calling a lemma that only has some specificational relevance, like it's computationally irrelevant. So you can mark that in F star as ghost, and then when we generate code, we won't generate code for it. Yeah.
What's your experience been with trying stuff at the SMT solver? Sometimes presumably it fails, you have to then do something to your program to
Yeah. Yeah. So the general mode. Okay. What's your experience with using the SMT solver? What do you do when it starts to fail? I guess is the question. And we take a lot of trouble to kind of help you get decent error messages from it. But sometimes SMT solver will time out, and you may not even get a good error message. At which point you interact with it by asking simple questions. You say, "Can you assert this fact? Can you prove this fact?" And then you debug the verification in this manner. I think we can do a lot. There's a lot of room to do better in this space. And even with robustness of an SMT solver, it turns out that there are small variations in the shape of a query can send it off the rails. So we struggle quite a lot with getting reproducible tests that always work in a certain amount of timeout and work well on different machines. I wish there were a better way to kind of force an SMT solver to go down that path to find a proof.
Thanks, Nick.